Alright, well, welcome to our lecture video for section 5.5. This section we're continuing to learn about infinite series, um, and we're going to learn another theorem that allows us to determine that a series is convergent. So let's jump right into that. Alright, so we're kind of going to recap what we already know to set us up for what we're learning in this section. Okay. Previously, we've seen that there are some series whose terms converge to zero as a sequence, okay, but the series itself is divergent. Okay, the first example that we ever saw of that was the harmonic series, which is just the series whose nth term is 1 over n. So 1 plus a half plus a third plus a fourth and a fifth, and it keeps going. The harmonic series is like that. The terms treated as a sequence do converge on zero, but when we add those terms up, the sum is infinity if we add up all infinitely many of them. So the series is not convergent, the series is divergent. Okay? But we've also seen that there are some classes of series where if the terms converge to zero, then the series is also convergent. Okay? Really, the only class we've really discussed like that so far is the geometric series. So remember, a geometric series has the form where the nth term is a times r to the n minus 1, where a and r are just constants. And we said previously that for geometric series, if we think of the terms as a sequence, then that sequence will converge to zero as long as the absolute value of r is less than 1. But in that case, not only do the terms converge to zero as a sequence, but it will also be the case that the series converges. And we even have a formula for getting the sum of that series, which is pretty nice. We'll review that later on. Okay. Most of our focus has been on just deciding whether the series is convergent or not. Usually we won't be able to know exactly what the sum is, but if we just know that it's convergent, then we can talk about approximating its sum and even sometimes get an idea of how accurate our approximation is. So in this section, we're going to be focusing on another class of series where the convergence of the terms to zero implies the convergence of that should say series right there. I'll fix that in the posted file later. Okay. So what I meant to say is we're going to look at another class of series where the convergence of the terms to zero as a sequence also implies that the series converges. Okay. And that's a pretty nice thing to pick up on. The reason it's nice is because it's very often pretty easy to see whether or not the terms go to zero. So if there's some additional conditions that would allow us to say yes, the series will converge, then we're in pretty good shape. Alright, so continuing on with our outline, we're going to look at the definition of the thing that this section is all about, alternating series. So let's have a look at page 496 of the book. Alright, so here's our definition of alternating series. It says any series whose terms alternate between positive and negative is called an alternating series. Okay, so an alternating series can be written in the form -1 to the n plus 1, okay, times some formula for the rest of the nth term. So the nth term is whatever b sub n is times -1 to the n sub 1, to the n plus 1. Okay, now remember, when we raise -1 to powers, even powers will make it positive, odd powers will make it negative, and so having a factor of -1 to a power at the front end is what creates this alternating effect. Now it can either be -1 to the n plus 1, which means that if n starts at 2, if n starts at 1, the power would start at 2. Okay, in which case we would start positive. -1 to the 2 is positive, but then -1 to the 3 is negative, and it just keeps alternating from there. Okay, but it's also okay for it to have the form of -1 to the just n times some formula b sub n for the rest of the term. That makes it so that the terms go negative, positive, negative, positive, instead of positive, negative, positive, negative. Either way, we would consider that to be an alternating series. Notice the note down here where the rest of the nth term, whatever that b sub n represents, has to be greater than or equal to 0, okay, for it to be considered to be in this form of an alternating series. Okay. Alright, so before we go any further, an example would be in order. So here's an example of an alternating series, a series that looks just like the harmonic series, except we've made the sign of the terms alternate, positive, negative, okay, positive, negative, and so on. But other than that, it's the terms of the harmonic series. Okay. It might not surprise you to know that we would refer to that particular alternating series as the alternating harmonic series. Okay. And because it is an alternating series, we can, when we write it in sigma notation, write it in one of those two forms mentioned in the definition. So if I want to put this into sigma notation, I'll say I've got a sum where n goes from 1 to infinity. Now, I'm either going to do negative 1 to the n or negative 1 to the n plus 1. Now, in this case, I'm going to go with n plus 1 because, and I'll look back at this real quick, because the first term was positive. Okay, if I want the first term to be positive, assuming that the series starts from n equals 1, then I need negative 1 to the n plus 1. If I had wanted it to go negative, positive, then I would just write negative 1 to the n rather than n plus 1. And then let me see, the rest of it is what the book was calling b sub n in the definition. That's just the formula for the rest of the term, not counting the sign. And in this case, that was just 1 over n. Okay. So if it's an alternating series, we can always write it in a form like this, where we've got negative 1 to the n or negative 1 to the n plus 1 times some formula for the rest of the nth term. Okay, and that formula is something that's non-negative. Okay. However, just because an alternating series always can be written that way doesn't necessarily mean that it would be explicitly written like that. Okay, here's an example. Okay, this series, I don't think it's immediately obvious that it's an alternating series, but if you start writing out the terms, I think it would be clear pretty quickly. Okay, if we think about this series here, series where the nth term is cosine of pi times n, when n is 1, my first term is just cosine of pi, and you might remember from trigonometry that cosine of pi is negative 1. So, when I write this series out, the sum from n equals 1 to infinity of cosine of pi n, the first term is 1, but then when I put in 2 for n, cosine of 2 pi, I'm sorry, I wrote the wrong thing. Cosine of pi is negative 1, but then when I put in 2 for n, cosine of 2 pi is positive 1. But then cosine of 3n is the same as cosine of 3 pi is the same thing as cosine of pi, which is negative 1. But then cosine of 4 pi is the same thing as cosine of 2 pi. So the fourth term is positive 1. Okay, and because cosine has a period of 2 pi, we're just going to keep flipping back and forth between negative 1 and positive 1 indefinitely. I guess I should say the next sign here would be subtraction. Okay. Now, this wasn't written in the form given in the definition, but now that I've written out a few terms, I could see how to write it that way. I'd say, hey, this is the sum from n equals 1 to infinity of negative 1. Now, since it starts negative, and goes negative, positive, negative, positive, I know that I just want negative 1 to the n. And in this case, that's actually all I need. Okay, apart from this thing that's giving me the negative 1 and the plus 1, I mean, I guess I could say b sub n is 1. Okay, but I don't really explicitly have to write that. Okay, now, here's why we're talking about alternating series. There's a theorem that tells us how to determine if an alternating series is convergent. So let's look at the alternating series test on page 498. Alright, theorem 5.13, alternating series test. So let's say we've got an alternating series fitting one of those two forms. So basically we've identified what's the rest of the term apart from, what's making it alternate. B sub n is the rest of the term. Okay, so remember b sub n is non-negative. It's greater than or equal to 0. It's the positive part of the term. You could think of it like that. So here's the deal. The test is telling us that that alternating series converges if, so there's two conditions here. One is b sub n plus 1 is always less than or equal to b sub n. Okay, which means it's a decreasing series. Whenever you go to the next term, the absolute value of the term is less than or equal to the absolute value of the last term. Okay, so that's one condition. Got to be decreasing. But then the other one is the limit of those terms. So notice we're not worrying about the negative 1 to the n or n plus 1. Just the limit of the positive parts of the terms. That's got to be 0. So there's two conditions to test, and if they both hold up, then the alternating series has to be convergent. Okay? There is a little note here that I think is worth remarking. They said that it had to be decreasing for n greater than or equal to 1, but actually it's good enough if we can show that it's decreasing for n past some point. So if it's always decreasing for n greater than or equal to 5, that's good enough. Okay, theorem still works. Alright, so let's look at this next example here on the outline. This is at the bottom of page 2 of our outline for section 5.5. Okay, it says for each of the series below, either use the alternating series test to conclude that the series converges, or state that the alternating series test does not apply. Okay, one thing to notice is that the alternating series test can be used to prove convergence, but it's not really a divergence test. Okay, either we can use it to prove convergence or it just doesn't apply. Now notice that in this case we're specifically saying not to write the proofs out. Generally, when you're asked to determine convergence or divergence, you need to write out your reasons in the form of a proof. But the exception to that is if the instructions say you don't need to do that. A lot of times the way the book will signify that you don't need to write out a proof is to say state whether it's convergent or divergent rather than show that it's convergent or divergent. But if you're ever unsure, you of course can ask me. Alright, so let's look at this first one. This is the alternating harmonic series. Terms look like 1 minus a half plus a third minus a fourth, and then so on. So I want you to notice two things about the terms. One is, if I ignore the signs, the absolute values of the terms definitely decreasing, but also definitely going to 0. Now if this was not an alternating series, that wouldn't be enough. Okay, without this part, if it was just the regular harmonic series, that's not a convergent series at all. But if it's alternating, that information is enough. Okay, that the terms go to 0 and that their absolute values are decreasing, that on top of the fact that it's alternating is enough to say that it's convergent. Well, let's see if I can spell convergent today. I think I need another R in there. Okay, now let's look at this next series here. We've already seen that that would look like -1 plus 1 minus 1 plus 1 minus, and it keeps going. Okay, now here's the deal. It's alternating, but my terms are not going to 0. I could technically say that they meet the first condition because it was decreasing but not strictly decreasing. Each term had to be less than or equal to the last term in terms of absolute value. Okay, and we got that condition, but they're not going to 0. Okay, in fact, if we cover up the signs, the terms are all 1s. Clearly not going to 0, they converge on 1. They're all 1. Okay, so the alternating series test does not apply. Test does not apply. And in fact, this was one of the first series we ever talked about. We didn't really write it in that form. We actually wrote it in this form when we introduced it back early in section 5.2. And what we said about it at that time was that, clearly the partial sums are not going to converge because every odd partial sum will be -1, but then every even partial sum will be 0. So the partial sums would keep flipping between -1 and 0. Actually, we might have looked at the version of this that flips between 1 and 0, but the idea was the same. Okay, this one is actually definitely not divergent. Not convergent, it's divergent. Okay, but the instructions just ask us to either conclude it's convergent by the alternating series test or just state that it doesn't apply. Okay. Now, look at this next one. This is actually problem 250 from the book. Okay, I just retyped it here. Now again, this is an alternating series. Okay, if I write these terms out, so let me see, if n is 1, that starts positive, and I would get 1/2, and then I would get minus 2/3, and then plus 3/4, and then minus 4/5, and then so on. So it is an alternating series, but you know what? The terms are not decreasing in absolute value. So the alternating series test does not apply. They're not going to 0 either. Okay, if I focus in on just the n over n plus 1, we know that as n goes to infinity, something like that would go to 1 over 1. The terms are going to 1. So neither of the conditions is met. Okay, neither of the additional conditions. The first condition really is that it's an alternating series, and then on top of that it's got to have terms whose absolute values are decreasing and terms whose absolute values are going to 0. Okay, those last two don't apply here, so we'll just say test does not apply. Okay, now one last one to look at here. Okay, this is actually kind of similar to that cosine one. It's not immediately obvious that it is even an alternating series at all, but when you start writing out the terms, let me see, when n is 1, we'd get sine of pi over 2. Well, that's 1. So 1 over 1 squared is 1. Alright, but then when n is 2, let me see, when n is 2, we'd get sine of pi. Okay, sine of pi is actually 0. Okay, sine of, when n is 2, we'd get sine of pi, that's 0. Okay, when n is 3, we'd get sine of 3 pi over 2. Sine of 3 pi over 2 is -1 over 3 squared, so that'd be -1/9. Okay. And then let me see. When n is 4, we'd give sine of 4 over 2 is 2. It'd be 2 pi. Okay. So sine of 2 pi is 0. And then let me see. Sine of, we'll do just a few more. When n is 5, we'd have sine of 5 pi over 2. But that's the same as sine of pi over 2. Okay, because it's just adding 2 pi. So that's back to 1, be 1 over 5 squared. So plus 1 over 25. And then I guess we'd have a 0, and then a minus 1 over 49, and it'd keep going. Okay. Well, let's see here. This is something I haven't specifically addressed yet, but these zeros don't really change the convergence. Okay, this doesn't really perfectly fit as I've written it in alternating series. Okay, but generally zero terms can just be ignored because they don't have any impact. So actually, we could rewrite it as 1 minus a ninth plus 1 over 25 minus 1 over 49. Okay, we haven't really lost anything by doing that. We've just tossed out zeros. When I write it in this form, now I can say, yeah, it's clearly an alternating series. The terms are clearly decreasing in absolute value and clearly going to 0. Okay, so in this case, I would say this one is convergent. Alright, so on to page 3 of the outline. This is the outline for section 5.5. Okay, in the last example we specifically said there was no need to write out a proof, but in this example we want to go ahead and formally write up a proof. Okay, use the alternating series test to prove that the series whose nth term is negative 1 to the n times n squared over 2 to the n is convergent. Okay, well, so the alternating series test has 3 requirements. The first is that it's an alternating series. Okay, we can see that that's true by inspection, so we might just acknowledge that. We can see by its form, no apostrophe in that form of the word its, we can see by its form that this is an alternating series. So if we're going to do a formal proof that a series is convergent using the alternating series test, we do need to at some point either show that it's alternating, or if it's clearly alternating, at least acknowledge that. Okay, because that's certainly a requirement of using the alternating series test. So we can, I meant to write the word see in here. We can see by its form that this is an alternating series. Okay, but we also need to show what? We need to show that the terms go to 0 and that they're decreasing. Okay, the absolute values of the terms. So from here on out, we're going to focus on this part here, the n squared over 2 to the n. The first part just gives us the signs, but the other conditions of applying the alternating series test rely on what the book is calling b sub n, the rest of it. Okay, so let's take the limit as n goes to infinity of n squared over 2 to the n. Okay, we need to show that this limit is 0. Now, as n goes to infinity, both n squared and 2 to the n, those are both going to infinity. Okay, so we've said previously that if you're computing a limit of a fraction and both the numerator and denominator are going to infinity, then you can apply L'Hopital's rule. So to apply L'Hopital's rule, we need to take the derivative of the top and the bottom and then see if we can compute our limit. Now the top is easy to take the derivative of. The top's just a polynomial. I mean, that's just about the first thing you ever learned how to take the derivative of. Bring the power down, decrease the power by 1, easy peasy. Now the bottom is an exponential function. That's a little trickier. We have discussed that in this class, but it hasn't come up a lot, so let me just kind of quickly review that. Okay, if I have 2 to the n, okay, I can rewrite that as e to the natural log of 2 to the n. Okay, because e to the natural log of anything equals that thing. These are inverse functions. But then I can use one of the rules of natural logs to say, hey, if I've got a natural log of something to a power, I can bring that power down in front of the natural log. Okay, so now I see that this is really a function that has the form of e to a variable times a constant. So in principle, this is kind of like f of x equals e to the 3x. You know, in that case, we know that the derivative is just the derivative of the 3x, okay, because we're applying the chain rule. We've got a function within a function. The inside function is 3x, okay, the outside function is e to the x. Chain rule says take the derivative of the outside function, which changes nothing because the derivative of e to the x is e to the x, but then multiply by the derivative of the inside function. So likewise, for f of x equals 2 to the x, which we've just seen could be rewritten as e to the x times natural log of 2, the derivative f prime of x would be, since this has that same form, it's basically just itself times natural log of 2. So e to the x times natural log of 2 times natural log of 2. Okay, and of course this part here was equivalent to 2 to the x. So f prime of x is 2 to the x times natural log of 2. And that's true in general. If I've got a positive constant raised to a variable power and I want to take the derivative, I just multiply by the natural log of that constant. Alright, so let's go back to what we were doing. We were applying L'Hopital's rule, and we were taking the derivative of the numerator and the denominator. Numerator was easy. Denominator is actually not too hard though, now that we have reviewed the rule. The derivative of 2 to the n is just 2 to the n times natural log of 2. Now, I'm taking a limit as n goes to infinity, and it's still the case that the numerator and denominator both go to infinity. So I can't resolve the limit yet, but if I apply L'Hopital's rule one more time, the top will become a constant, and then we'll be good to go. So, applying L'Hopital's rule one more time, this becomes the limit of just 2 over 2 to the n times, alright, since I differentiate again, I'll multiply by natural log of 2 again, so I'll just square it. Okay, now only the denominator is going to is going to infinity. So now I can say that the value of the limit equals 0. Okay, so that's the second condition, second of 3 conditions. First condition for applying the alternating series test is that it is an alternating series. That's usually pretty easy to check off. Another condition is that the limit of the absolute values of the terms as n goes to infinity is 0. We got that. But then we need to know, this is our last condition, we need to know that the absolute values of the terms are decreasing. So let's look at them. Let me see, when n is 1, n squared over 2 sub n would be, it'd be 1 over 2 to the 1, so it'd be 1/2. when n is 2, n squared over 2 to the n would be, and let me see, 2 squared is 4, 2 to the 2 is 4 again, so 4 over 4 is 1. Alright, well that's not a good start, because we want them to be decreasing. Okay, and in fact, right off the bat, they're increasing. But remember we said that it's good enough if they're eventually decreasing. Okay, so let's keep going. Okay, I have a hunch that they're going to be eventually decreasing, and here's why I think that. I know that this fraction goes to 0 as n goes to infinity. So it seems like at some point it's got to turn and go to 0. Okay, let's see what happens here. If n is 3, I would have 9, 3 squared is 9, 2 to the 3 is 8. N squared over 2 to the n would be 9/8. Well, that's a little bigger than 1. Although notice that's not as big of a hop. Instead of going up by a half, we only went up by an eighth. That's encouraging. Alright. If n is 4, then 4 squared would be 16, and 2 to the 4 would also be 16. 16 over 16 is 1. Alright. This is definitely what we were looking for. It stopped increasing and it started decreasing. Hopefully, it would continue decreasing from here on out. And if we can show that it would continue decreasing, then we can say, hey, as long as it decreases for all n past 3, that's good enough. That last condition is still met. But how do we show that it's going to keep decreasing indefinitely? Well, you actually do have a mathematical tool at your disposal that we haven't really used for this purpose, but you could use for this purpose. And that tool is something you learned in Calculus 1, okay, called, we didn't really quite give a name to it, but the notion was that if the derivative is negative, it must be decreasing. We use that as part of something called the first derivative test, but the first derivative test was just a little bit more than what we're going to do here. So let's think about the continuous function f of x equals x squared over 2 to the x. Okay, if we can show that this derivative is negative past a certain point, then we can say definitively the function is decreasing past that point. Now, you might remember that to take the derivative of a function that is a quotient, you have to use the quotient rule. The quotient rule says you take the derivative of the top, okay, the numerator of the fraction, you multiply it by the bottom, and then you subtract, and you take the numerator times the derivative of the bottom, the denominator, and you put all of that over the denominator squared. That's the quotient rule. Alright, so let me see. That would be 2x times 2 to the x minus x squared times, remember when we took the derivative of 2 to the x, that was 2 to the x times natural log of 2. And 2 to the x squared is just 2 to the 2x. Alright, well, I know that looks like kind of a big mess, but we can simplify that. In particular, let's factor out what we can. Okay, I can see here that I could factor 2 to the x out of, this is all one term and this is all one term. We can take 2 to the x out and we can take x out. So let's take those things out. So 2 to the x and an x. In the first term, that just leaves a 2. And in the second term, that just leaves an x and a natural log of 2. and then the bottom we just have 2 to the 2x. Okay. Now here's the thing. Since we're only worried about n being greater than 1, we only have to worry about x being greater than or equal to 1. Okay. So, assuming that x is greater than or equal to 1, 2 to the x, well 2 to the x would be positive no matter what, but 2 to the x, x, and 2 to the 2x are all positive. So I mean that takes care of this factor, that factor, that factor. They're not really gone, but we know they're all positive. Positive, positive, positive. The only thing that's really in question is the 2 minus x times natural log of 2. Okay. So let's think about that one. Let's phrase it like this. For what values of x is two minus x times natural log of 2. Well, what question do we want to ask here? Here's what we want to know. We want to know, is this factor ever negative? Because if it's not, then the whole derivative's never negative, and this is kind of a lost cause. Because if the derivative's never negative, we're not going to be able to show that it's decreasing. Okay, so maybe what we want to know is, for what values of x is this factor less than 0? Well, that's now just an algebra question. Okay, 2 minus x natural log of 2 less than 0 would be true if and only if, so I'll just move this term over. 2 is less than x natural log of 2. And now I'll divide by natural log of 2. Natural log of 2 is a positive number. Let's check that real quick. Natural log of 2, yep, it's 0.69. Positive number, that's important because I'm about to divide by it. If it's negative, I'm going to have to flip this. But it's not negative, so I'm good. Alright, so 2 over natural log of 2 is less than x. Aha! What is 2 over natural log of 2? 2 divided by natural log of 2 is 2.88. So that's true if and only if that's true, which is true if and only if 2.88 and change, whatever it was, is less than x. Okay, well that basically means x would be greater than or equal to 3. Aha! So this factor is negative, less than 0, if and only if x is greater than or equal to 3. Okay. But since everything else was positive, we can say that for x greater than or equal to 3, this factor is negative, which means the derivative is negative. Haha! Now we're in business. So, for x greater than or equal to 3, f prime of x is negative, which means f of x is decreasing. Okay, so now we can go back to thinking about n's instead of x's, and we can say, so for n greater than or equal to 3, n squared over 2 to the n is decreasing. Okay, so what we've done is we've shown that all of the conditions of the alternating series test are met. That the series is alternating, that the absolute value of its terms goes to 0, and that the absolute value of its terms is decreasing past a certain point. So now we can state what test we're using. Should be obvious, but we'll go ahead and say it. Okay, so by the alternating series test, and then finally we'll state our conclusion. Okay, because all its conditions were met, we can use the alternating series test to conclude that our series, where n goes from 1 to infinity, and it looks like negative 1 to the n times n squared over 2 to the n, is convergent. Alright, so back to the outline. This is page 3 of our outline. Okay, it's time to make an important point about the types of convergent that an alternating series can be. Believe it or not, there is more than one type of convergent, and sometimes the distinction is pretty important. Okay, so notice that we have some convergent alternating series. So like here's an example. Let's say that it was an alternating series that looked like the nth term was negative 1 to the n plus 1 times 1 over n squared. Okay, that definitely satisfies the alternating series test because it's an alternating series and the absolute values of the terms are decreasing and going to 0. So it's definitely an alternating series, but notice that even if it wasn't alternating, it would still be a convergent p-series. So notice that this one would be convergent even if we made all of the terms positive. Okay, we would call a series like that absolutely convergent. And the absolutely refers to absolute value. I mean, basically, if I toss out this part, I'm effectively taking the absolute values of the terms. I'm making them all positive. So if a series is convergent, but it would still be convergent even if we took the absolute values of all the terms, we say it's absolutely convergent. Now, let's contrast that to another convergent alternating series, one that's almost the same, except instead of having an n squared in the denominator here, we just have an n. Now, it's still the case that if we think about the absolute values of the terms, those absolute values do go to 0 and they are decreasing. So by the alternating series test, this is a convergent series. But it wouldn't be convergent if we made all the terms positive. If we make all the terms positive, then it's a divergent p-series. It's the harmonic series. Okay, so this one is convergent as an alternating series, but it's not convergent if we make all the terms positive, if we take their absolute values. Okay, a series like that is what we call conditionally convergent. Alright, let's look at some definition and theorem in the book on page 500. Alright, so here's a definition on page 500 of the book. Okay, it's basically just covering what we were just talking about. A series exhibits absolute convergence if, when you apply an absolute value to all its terms, it converges. A series exhibits conditional convergence if the series is convergent, but if you take the absolute values of its terms, it's not convergent, it's divergent. Okay? Now, here's an important theorem. Okay? Theorem 5.15, bottom of page 500. Okay, the theorem is that if a series is absolutely convergent, then it's convergent. So if it would be convergent if you made all the terms positive, then it's convergent. That's actually a pretty useful theorem, and I'll tell you why. The reason it's useful is because we get a lot of alternating series when we start trying to um, generate series that are um, polynomial approximations of transcendental functions. That's what we're going to be doing in the next chapter. That's what's driving a lot of what we're doing in this chapter, and that comes up a lot. But a lot of the tests for convergence that we've learned in this series, this chapter, rely on all the terms being positive. So a lot of times we'll look at a series and be able to say, hey, I would know that it's convergent if all the terms were positive, because I'd know how to test it. Well, this theorem is saying that if it would be convergent if all the terms were positive, then you know it's convergent. Okay, if it's absolutely convergent, it's regular convergent. But what we've just seen is that sometimes you're regular convergent and not absolutely convergent. That's what we call conditional convergence. So absolute convergence is actually a stronger condition than conditional or regular convergence. Absolute convergence implies regular convergence, but regular convergence doesn't necessarily imply absolute convergence. Remember, we said before, the truth of a statement doesn't really imply the truth of its converse. Okay, here the statement is, if you're absolutely convergent, then you're convergent. The converse would be, if you're convergent, then you're absolutely convergent. But that isn't always true. That's why we have this term conditional convergence. Okay. Now, one thing I do want to just kind of mention is that if we're looking at a series that's all positive terms to begin with, if that series is convergent, then it's automatically absolutely convergent. Okay, because taking absolute values wouldn't change anything. So it's really just in series where the terms are some terms are positive and some are negative, that we could have conditional convergence. All right. All right. So let's apply this theorem we've just learned about how absolute convergence implies convergence, and what it means to be absolutely convergent or conditionally convergent. Let's apply that to some problems in the book. So I'm going to look at problems 251, and then 252, and then also 275. They all have the same instructions. Notice the word state. The word state is the book's way of saying, we don't need you to do a proof, we just want you to figure out the answer. Sometimes that's okay. Okay, again, you got to go by the instructions. State whether each of the series converges absolutely, or converges conditionally, or doesn't converge at all. All right. So let's start with 251. It's an alternating series. Okay, this little -1 to the n plus 1 tells me that. Okay, but then when I look at the rest of it, I have square root of n plus 1 over square root of n plus 3. So the degree of the top is 1/2. The degree of the bottom is 1/2. So if I were to take the limit of this fraction as n goes to infinity, since the degrees match, I would have to go coefficient over coefficient. The limit would be 1. Well, you know what? If the limit is going to 1, then we can't apply the alternating series test. To apply the alternating series test, we would need the terms to be going to 0, the absolute values of the terms, what you would have without this part. But since they're going to 1, essentially this is eventually becoming basically an alternating series of 1s and -1s, okay, or numbers that are converging on 1 and -1, which means that my sum is just going to flip around. So this is not going to be convergent at all. This is divergent. Now, let's look at 252. Okay. It's an alternating series. So again, let's focus on the rest of the nth term. Okay. I have 1 over the square root of n plus 3. Okay, that is similar to a p-series with a p-value of 1/2. If I did a limit comparison test, I would wind up concluding that this is a divergent p-series. Okay, so it's not going to be convergent if it's not alternating, but it is alternating. So since it's alternating, all I really have to think about is, do the absolute values decrease and go to 0? Well, they do decrease and go to 0. So as an alternating series, it is convergent. But without that alternating part, it's not convergent. It's similar to a divergent p-series. So it's convergent, but it's not absolutely convergent. This is conditionally convergent. All right, one more. Let's look at 275. Again, we're just being asked to make statements. We don't have to write out full proofs here. But it's our job to state whether it is absolutely convergent, conditionally convergent, or divergent. So I see it's an alternating series. So now I can kind of mentally set that aside and focus on the rest of the nth term. So my formula for the nth term is 1 over n minus 1 over n plus 1. Well, you know, it's been a while since we've talked about one of these, but setting aside the signs, this is a telescoping series. So let's actually think about just the series without the signs. Alright, so I've rewritten the series from problem 275 without the -1 to the n plus 1. Okay, that effectively takes the absolute values of the terms. So I'm going to think about this series. If this series is convergent, then I can say, hey, it's convergent even when I take the absolute values, and so it would be absolutely convergent. So this series of absolute values, basically just the positive parts of the terms, looks like this. When n is 1, I would get 1 minus a half. That's my first term. When n is 2, I'd get a half minus a third. When n is 3, I'd get a third minus a fourth, and so on. Now, I could simplify each one of these to one fraction, but I like writing it this way better because then I can see the cancellations. Minus a half plus a half, minus a third plus a third, minus a fourth plus a fourth, minus a fifth plus a fifth, and I can see that everything's going to cancel except this 1. Okay, that means that the entire value of the sum of this series is 1. Okay, so this series, where the nth term is 1 over n minus 1 over n plus 1, is convergent. Here's what that tells me. That means that the original series we had, I think I can write it here. So here was the original series in 275. Where'd I put that? Yeah, it was an n plus 1. -1 n plus 1 times 1 over n minus 1 over n plus 1, like that. It means that this series is absolutely convergent. Is absolutely convergent. Which is the answer we were looking for. Okay, the idea is that if I took the absolute values of the terms of this series, all that would do would be it would squelch this part, and so I would get this series, but that series converges to 1, So the original alternating series is absolutely convergent. It's convergent even if you take the absolute values of its terms. And then of course if it's absolutely convergent, it's also regularly convergent. So if we needed to be able to say this series was convergent, now we can. But really, based on our instructions, we wanted to make this stronger statement that it's absolutely convergent. Alright, we're on the home stretch for section 5.5, but we've got one more thing to discuss, and this is really kind of closing the loop from something we brought up at the beginning of this section. Okay, it's the notion that often we can show that a series is convergent, but we can't figure out exactly what its sum is. But that still has value, because if we know it's convergent, then we can approximate its infinite sum using a partial sum. However, approximations are really only useful if we can get some idea of how good they are. Okay, if we can get kind of a maximum amount of error that there could be, then we can decide whether or not the approximation is close enough to be useful. So let's think about the alternating harmonic series again. Okay, this is the example at the bottom of page 3 at the outline, but it carries over to the fourth and final page of the outline for section 5.5. So we're going to approximate the infinite sum of the series by computing the fourth partial sum. And then we're going to determine an upper bound for the sum of the remaining terms of the series. Okay, well, the fourth partial sum, remember we use a big S for partial sums, would just be the sum of the first four terms. We're talking about the alternating harmonic series, so it's 1 minus a half plus a third minus a fourth. So I think I could probably do that in my head even. 1 minus a half is a half, plus a third, a half plus a third is 5/6, minus a fourth, you know what? It's getting late, I'm tired, a decimal would probably be better anyway. 1 minus a half plus a third minus a fourth, 0.58333. Now, that's an approximation for the sum of the entire series. Okay, I can say that because I know the entire series is converging on some number. So if I add up any number of terms, I'm starting to get near that number. But the question is always, how near am I? If I'm pretty close, this might be a useful approximation, but I don't know if I'm close or not. However, with alternating series, it turns out to be really easy to get a sense of how far off you might be. Okay. We've talked about this once before, where we used an integral to get an idea of how far off we might be with a partial sum, but it's even easier with alternating series. I mean, let's think about the rest of the terms, the ones we left out. The terms we left out are 1/5 minus 1/6 plus 1/7 minus 1/8, and then it keeps going. So if I were to continue adding terms on, this was my fourth partial sum. To get my fifth partial sum, I would add 1/5 to that number, which would increase it. And then for my next partial sum, I would subtract 1/6. That would decrease it, but it would never decrease it as low as it was after just four terms, because 1/6 doesn't have as big of an absolute value as 1/5. So it would go up, and then it would come down, but it wouldn't come past 0.583. And then it would go up again, but it wouldn't go up as high as it was even before I subtracted 1/6. Okay, because 1/7 is less than 1/6. So 1/7 can't even get me back to where I was before I did this, which means that however high it takes me, it won't take me higher than I was at 1/5. and then I'll subtract 1/8. That brings me back down, but it doesn't even get me down as far as I was at this point because 1/8 is less than 1/7. So if this was my starting point, it's like I went up, and then I came down, and then I went up and down. But each time I go up, I'm not getting as high as I was before, and each time I come down, I'm not getting as low as my last low point. So I just keep zigging and zagging up and down, but less and less. And I'm never going to get any further away from this point than I was on that first trip up. So here's the thing. I can say definitively that this number was not off from the entire sum of the whole series by any more than 1/5. 1/5 is an upper bound for the remaining terms. But that means that it's an upper bound for the error if I let this partial sum be my approximation of the entire sum. And I can always do this for an alternating series. Anytime I make an approximation of the sum of a convergent, has to be convergent, alternating series using a finite number of terms, assuming that it's the type of alternating series that we've been applying the alternating series test to, i.e. the kind where the terms are decreasing and going to 0, then I can say that my error from approximating with 4 terms or n term, it doesn't matter, is no more than the absolute value of the next term. And that's going to give us our last theorem on page 499. Alright, so here's the last theorem we're going to discuss for section 5.5. It's the remainders and alternating series theorem. So, consider an alternating series that has one of these two forms from our definition of alternating series. And notice that it has to satisfy the hypotheses of the alternating series test. So that means that the b sub n's, those have got to be going to 0 and decreasing. Let S denote the sum of the entire series, all of the infinitely many terms. And S sub capital N denote the nth partial sum. Okay, so for any integer big N greater than or equal to 1, the remainder R sub n, which would just be the difference between the infinite sum and the partial sum, satisfies this little inequality right here. The absolute value of the inequality is less than or equal to the first term that we left out of our partial sum, which means that our error is less than that. Okay, so let's see how we can apply that to a problem in the book. And in fact, here's the problem we're going to look at. We'll just scroll right down there while we're on this screen. Problem 283. So, what are they giving us here? They're giving us the b sub n part. Ooh, I highlighted the wrong one. They're giving us the b sub n part of an alternating series. Okay, what do the instructions say? The instructions say, in each of the following problems, use the estimate remainder. So this is the thing from the theorem we were just looking at, to find a value of n that guarantees that the sum of the first n terms of the alternating series differs from the infinite sum by at most the given error. Okay, calculate the partial sum for this n. Alright, so here's the error. We want the error to be less than 10 to the negative 6, and it's an alternating series where the absolute values of the terms are 1 over 2 to the n. Alright, got it. Alright, so here's our series that was being referenced in problem 283. It's an alternating series, okay, where the absolute value of the nth term would be 1 over 2 to the n. and they want us to approximate the sum of the alternating series with an error that's less than 10 to the negative 6. And of course 10 to the negative 6 is the same thing as a decimal number, where we have after the decimal point 5 zeros and then the 1 is in the 6th place. But according to the theorem we were just looking at, the error would have to be less than the absolute value of the first term that we leave out. So let's just say if we are going to approximate the sum with, all right, we don't know how many we need yet, so we'll just be generic, big N. If we are going to approximate the sum with big N terms, the error is less than, it's less than the absolute value of the first term we leave out. So if we're going to take the first N terms, then the first one we leave out would be 1 over 2 to the N plus 1. Okay, our error is going to be less than that. So if we make that less than 10 to the negative 6, that'll make our error less than 10 to the negative 6. Okay, so we only has one E in it. We need this to be true. We need this to be true. We need the 1 over 2 to the N plus 1 to be less than 10 to the negative 6. Well, you know what? That shouldn't be too hard to work out. We just need to do a little algebra there. So let's do the algebra. It looks like I need to bring this 2 to the N plus 1 up and the 10 to the negative 6 down. So rearranging, I get 1 over 10 to the negative 6 is less than 2 to the N plus 1. And it looks like I'm going to need a little more paper there. So here's what I just had. 1 over 10 to the negative 6 is less than 2 to the big N plus 1, like that. But of course 1 over 10 to the negative 6 is the same thing as just 10 to the 6. Now, the thing that I'm trying to isolate is up in an exponent. So essentially the right-hand side is an exponential function, which means that to get this thing out of the exponent, I'm going to have to use the inverse of an exponential function, which is a log function. Okay, and I'll just apply a natural log to both sides. Natural log of 10 to the 6 is less than natural log of 2 to the N plus 1. And the reason this is helpful is because now I can use the rule that says if you've got a log of something to a power, you can move that power down front. Alright, so natural log of 10 to the 6 is less than the quantity N plus 1 times natural log of 2. So now I just need to move some stuff around and I'll have N isolated. So I need to divide by natural log of 2. We checked earlier that natural log of 2 is negative, so we don't need to flip that. So natural log of 10 to the 6th over natural log of 2 is less than N plus 1. And I guess we just subtract 1 and N will be isolated. So natural log of 10 to the 6th over natural log of 2 minus 1 is less than N. Well, at this point we're going to need the trusty calculator. So clear all that out. We're going to do natural log of 10 raised to the 6 divided by natural log of 2 and then subtract 1. So I get 18.9. Alright, so that means that 18.9 and change needs to be less than N. So That means n needs to be greater than or equal to 19. Okay, so what we've just shown is that if we do our partial sum of this series with 19 terms, that'll give us an approximation to the whole infinite sum that is off by less than a millionth. So let's do the 19th partial sum, which is just the sum from n equals 1 to 19 of negative 1 to the n plus 1 over 1 over 2 to the n. Now, since there's only 19 of them, it would be doable to punch that into the calculator. But I think this would actually be a good one to use Desmos for. So let's have a look at Desmos. Alright, now here we are in Desmos. Now obviously, you can't use this stuff on an exam. So on an exam, if I asked you to do a partial sum, it'd probably be a smaller one. But in practice, to really be useful, we have to be able to add up larger partial sums. And it's pretty easy to add up a partial sum of just about any size if you have some type of computing technology that is either designed for that or that you can program a little loop into. Desmos is designed for this. If I type in SUM, it knows I want a sum, and then I can tell it, hey, I want a sum from 1 to 19. And then I just have to type in my formula here. So I need a negative 1. I can use my caret, shift 6, to get up into the power. Although, one thing about Desmos, if I want to do n plus 1 as a power, for whatever reason, when you hit plus, it automatically kicks you out of the power. But you can get around that by putting the power in parentheses. And then you can go back and add your plus 1. Alright, and now I'm back out of the power by arrowing over. I need a 1 over. Let's do multiplication so it keeps the fractions separate. 1 over 2 caret n. Alright, it gives me 0.33, how many 3's there? 333, 333, 969, 116. Alright. Makes it seem like if that's an approximation of the sum, that the entire infinite, especially if we know our approximation should be off by less than a millionth, makes me wonder if the whole sum might be a third. Now, here's the thing. Normally, we would have no way of knowing. That's the whole point of doing an approximation. We don't know exactly what the value of the infinite sum is. But in this case, we actually can know. Let's have a look at that. Alright, here's a formula that we learned back in section 5.2, and it's actually kind of nice that we get a chance to review this. We haven't mentioned it in a while. But it's a formula for the sum of an infinite geometric series if the r value has an absolute value that's less than 1. Okay, if you've got an infinite geometric series of the form a times r to the n minus 1, and the absolute value of r is less than 1, then the sum of that series is a over 1 minus r. And as it happens, this alternating series that we've been looking at in problem 283 is, in fact, a convergent geometric series. Now, we're going to have to rewrite it a little bit. Okay, 1 over 2 to the n is 1/2 to the n. Okay, and this part here, the negative 1 to the n plus 1, I can split out one factor of negative 1 there and have negative 1 to the n. Okay, well, let me see. What else do I want to do? I want to try to get it to match this. So I need to split out a factor of 1/2 to get this down to, I need to get this down to 1/2 to the n minus 1. And so I need to split out another negative 1 out of this. So negative 1, I'll split out another negative 1. That gives me negative 1 to the n minus 1. And if I split out a factor of 1/2, that'll leave me a 1/2 to the n minus 1. And then these two things that have a power of n minus 1, I can combine those. So that's going to give me a, well, let me see. I've got a negative 1 and a negative 1. That's a positive 1 and a 1/2. So a 1/2 times, and then these two things I can combine. Since they have the same power, I can go ahead and multiply them and say, hey, that's negative 1/2 to the n minus 1. And now that's in the correct form for a geometric series. I can identify the a and I can identify the r. A is 1/2, r is negative 1/2. So I can apply the formula that says that this would be equal to a over 1 minus r. So 1/2 over 1 minus negative 1/2. Now check this out. This is kind of cool. That would be equal to, pull that back a little bit, 1/2 over 3/2. And if I flip this bottom fraction, the 2's are going to cancel, and I get 1/3. That's the exact value of the entire infinite sum of the series that we're talking about in 283. So if I go back into Desmos and I look at my approximation that was supposed to be good, at least to an accuracy within a millionth, I'd say we got it. Looks pretty good to me. Pretty good. True value is 1/3, and we were pretty close to 1/3. Alright. Well, let's go ahead and shut that off and turn this back on. We are now at the end of section 5.5. I'm going to go ahead and wrap it up here. As always, I want to encourage you, if you have questions about anything, reach out to me. We can set up a Zoom session and go over whatever you want to go over. Alright, well, again, let me encourage you, stay safe, stay healthy, stay home as much as you can, and I hope to see you all again as soon as possible. Take care, everybody.